On the 16th of July 1969, the Saturn V rocket carrying Apollo 11 launched from Kennedy Space Center. Humanity was about to set foot on the moon. The Saturn V was the most powerful launch vehicle ever built, hands down. It had 7 times the lift capacity of the Soviet Union's strongest rocket at the time, the Proton K. It ran on liquid hydrogen as fuel and liquid oxygen as the oxidizer. Even today, modern liquid-fueled rockets still rely on that same LOX and LH2 combo as their main propellant. Before launch, the two components are kept separately. Once it go time, they pumped into the combustion chamber where they mix and trigger a massive chemical reaction, creating a huge burst of thrust that sends the rocket blasting off into the sky. There is actually a common little bug that figured out how to do rocket propulsion 400 million years before humans ever dreamed of building rockets. And get this, its internal chemistry setup is even more sophisticated than the Saturn V. Today we're diving into this wild little creature scientifically known as the bombardier beetle, but most people just call it the fart bug. The term fart bug is actually a nickname for over 500 different species of beetles, all part of the ground beetle family. They are further grouped into subfamilies like Brachynae, Posinae, Ozaninae, and Mitrophorini. Yeah, try saying those 5 times fast. These bugs live on every continent except Antarctica, and they're nocturnal, meat-eating, and love to hunt solo, though they are technically social insects. But here is the real kicker. When they feel threatened, they can blast a hot, stinky chemical spray straight out of their butt with a little pop sound for dramatic effect. It's like they are firing a tiny stink grenade. That's how they got the nickname fart bug. In the summer of 1955, a young entomologist was kneeling on the ground, digging through rocks in search of something useful for his research paper. Excited, he reached out to grab one, and suddenly, it let out a sharp popping sound. But the beetle responded with a series of sharp pops, followed by a burning sensation in his fingertips and a foul stench filling the air. At that moment, he had no idea that this accidental encounter would shape the rest of his life. That young man would go on to become a legendary figure in chemical ecology, Thomas Eisner, the mad genius of insect science, and the little creature that fired the first shot, none other than the bombardier beetle, the chemical weapons expert of the insect world. Thomas Eisner is often called the father of chemical ecology. The European Space Agency even created a Founders Award in his honor. The U.S. National Academy of Sciences gave him the Joan Carty Award, and President Bill Clinton personally awarded him the National Medal of Science. His main focus was how insects use chemistry to defend themselves against predators, and his most famous discovery was figuring out exactly how the bombardier beetle pulls off its explosive defense. You could say he was the dark arts master of entomology, studying all sorts of venomous creatures, like scorpions, centipedes, spiders, and wasps. To him, they were like scientific pets. He also loved watching how insects live, fight, mate, and kill. And from the insect's perspective, this brilliant, quirky scientist probably seemed like some kind of monster of destruction. Later in life, Eisner joked that Parkinson's disease had taken away his ability to hold and handle his beloved insects. Maybe as a result of decades spent working with their defensive secretions, or maybe just karma for poking, stabbing, and squishing so many bugs over the years. He believed in natural selection. But even after a lifetime of study, he never found any evidence in bombardier beetles that fully aligned with the theory of evolution. And maybe that's the mystery Eisner left behind for the rest of us. To get to the bottom of how the bombardier beetle defends itself, Eisner and his research partner Gerald spent over a decade and a ton of research funding, tracking down and studying these beetles from all over the world. Countless little beetles ended up locked in cages, shipped on every kind of transportation imaginable to Cornell University, where they waited confused and clueless for their turn with these two bug-obsessed scientists. Funny enough, when you put their nicknames together, Tom and Jerry. It just happened to match the name of the hit cartoon that was big at the time. Together, they published over 130 scientific papers and uncovered the structure and function of kinds of defensive secretions, everything from natural glue, aphrodisiacs, pigments, to chemical signals known as pheromones. One spring day near the Archbold Biological Station in Florida, a group of Galerita lecontae was dozing peacefully. Suddenly, a beam of purple light shot down from the sky. Startled, the beetles scattered in all directions, but there was no escaping. They were all captured, along with a close cousin from the same tribe, G. janus. To their surprise, life in captivity wasn't all that bad. There was an endless buffet of mealworms and fresh water, and after a few weeks they had even put on some weight. But just when things started to feel comfortable, bam! They got thrown into a bucket of ice water, frozen half to death, and even their proudest weapon couldn't fire anymore. Eisner took a metal hook, fixed it to the beetle's elytra using a drop of melted wax, then hung the beetle upside down from the end of a copper rod. That's when Tom and Jerry started stirring things up. As the beetle slowly came back to life from its frozen state, it suddenly felt something clamping down on its legs. Instinctively, it fired off its ultimate weapon. With a loud pop, a burst of foul-smelling corrosive gas shot out, filling the air in an instant. Eisner was beyond thrilled because he had just captured the beetle's precision strike on camera and recorded the whole thing with test paper. Analysis confirmed that both types of beetles released a spray containing formic acid at 80% concentration. In addition, it also contained acetic acid and 19 lipophilic compounds, with almost no water content. That's why, whenever someone picks them up in the field, they always give off that nasty, unmistakable chemical stench. But Eisner's obsession didn't stop there. He didn't just study how these beetles eat, poop, and mate. He even petted them. He'd fight through the eye-watering stench, carefully sniffing their body odors like some kind of chemical connoisseur. You have to wonder, for a beetle that's a literal master of chemical warfare, getting handled like that must have felt like the ultimate humiliation. If beetles could feel shame, the bombardier beetle probably wanted to just drop dead right then and there. To figure out whether that burning sensation from the beetle spray was caused by corrosive chemicals or just intense heat, Eisner brought in some gear and ran tests. Turns out the spray hits 100 degrees Celsius, so yeah, this little guy's packing a double buff: heat and acid. Its ultimate attack is maxed out and basically unstoppable. Eisner went even deeper, using phase contrast microscopy to dissect the beetle. Inside its abdomen, he found two defensive glands, one holding hydroquinone, the other hydrogen peroxide. These two chemicals mix inside a chamber loaded with catalase and peroxidase enzymes. The hydrogen peroxide, broken down by the enzymes, releases oxygen, which oxidizes hydroquinone into benzoquinone. The reaction is so intense and exothermic that it causes the liquid to boil and vaporize. And, with a burst of oxygen pressure behind it, the beetle blasts the hot mixture up to 20 centimeters away. To truly understand what it feels like for a predator to eat a bombardier beetle, Eisner went as far as putting one in his own mouth. The moment those chemicals exploded inside, the burning, corrosive blast mixed with that nasty, eye-watering stench, yeah, that experience stuck with him for life. For the next few days, even his co-workers didn't really want to talk to him. Eisner also found that Galerita beetles could precisely aim their chemical blasts at each individual leg or antenna. In beetles that had been disturbed for 3 months, he observed they could fire 5 to 9 bursts of formic acid from their glands. That's around 4.5 milligrams each shot, roughly 3% of their body weight. Once depleted, it took about 37 days to fully replenish the formic acid reserves. Each blast used up 0.7 milligrams of formic acid and required 5.5 days and 9 milligrams of protein to recover. Even for bugs, it turns out war comes at a cost. While flipping through Darwin's memoirs, Eisner came across a passage that seemed like it might have been describing a bombardier beetle. One day, Darwin peeled back a piece of tree bark and spotted 2 beetles underneath. He grabbed one with each hand, then saw a third beetle show up, trying to free up his other hand. Darwin did what any overly enthusiastic naturalist might do. He popped the first beetle into his mouth. That's when it blasted out a stream of stinging, acidic chemicals. Instantly, Darwin felt a burning pain on his tongue and got super nauseous. He spat the beetle out on reflex. But by then, all 3 beetles had escaped. Eisner wasn't 100% convinced it was a bombardier beetle, because theoretically if it was, Darwin would have gotten blasted the second he picked it up, not after sticking it in his mouth. To dig deeper, in 1982, Eisner actually took a trip to Darwin's home in Kent, and there in the old beetle collection, he really did find a pinned specimen of a bombardier beetle. Eisner also described another one of his wild experiments. This time, the star of the show was an African bombardier beetle from Kenya. Just like its cousins, this poor little guy suddenly found himself dropped into a tub of ice water, frozen stiff, completely helpless. Its defenses totally shut down. Then Eisner pulled out his classic move, and, while the beetle was probably screaming in insect language, he gave it a full-body inspection, free of charge. From this, Eisner came to a new conclusion. The African bombardier beetle is on another level. This guy came loaded with top-tier gear, like the elite version of chemical warfare. It could aim at each individual leg, and not just the leg, but specific segments, by automatically twisting its cannon. It didn't even need to turn its body to face a threat. Instead, it could just swivel the nozzle itself, allowing it to spray in almost any direction, even straight forward, parallel to its back. The beetle's raised elytra work like a guidance system, a real-life demonstration of the Coanda effect, straight out of aerospace engineering. And when it targets a specific leg, it actually adjusts for the leg's position and angle just to maximize the accuracy and efficiency of the spray. The chemical blast hits a scorching 100 degrees Celsius, packed with highly concentrated, irritating compounds like p-benzoquinone. It can fire up to 20 times before its glands run dry, and even then, it only takes 5 to 14 days to fully recharge. Clearly, this beetle was way more hardcore than the stand-in fake bombardiers from Eisner's earlier tests. But due to the limits of tech at the time, some questions remained unanswered. Like, how does the beetle withstand its own blast? How does it not get burned or hurt by the heat and chemicals it's firing? And so just like that, Tom and Jerry spent years, literally years, geeking out over bombardier beetles. They were totally hooked, obsessed with every little detail of these explosive bugs. Eventually, they published 2 landmark papers in the Proceedings of the National Academy of Sciences. One was titled Defensive Production of Formic Acid, and the other Spraying Aiming in the Bombardier Beetle. These 2 papers pretty much cemented their status in the scientific world, making Tom and Jerry some of the founding pioneers of chemical ecology. In Eisner's book, For Love of Insects, the bombardier beetle literally gets top billing, front and center, which just shows how deep his obsession ran. He even personally shot a film called Secret Weapons, which went on to win Best Science Film from the British Association for the Advancement of Science. And get this, Eisner actually framed the rejection letter he got when he first applied to Cornell as an undergrad and hung it on the wall of his Cornell office. Yeah, kept it up there for over 50 years, didn't care if it made the university brass uncomfortable. But hey, when you're a brilliant weirdo like Eisner, awkwardness probably just rolls right off you. Ever since Eisner published his groundbreaking research, more and more scientists around the world started diving into the mysteries of the bombardier beetle. For example, Japanese researchers ran a pretty wild experiment. They put frogs in a lab and watched what happened when they tried to eat these beetles. Here's what they found. 92.9% of frogs, straight up, refused to swallow a live bombardier beetle. 67.9% gave up the moment their tongue touched it. 25% actually swallowed the beetle, but then instantly spat it right back out. Only 7.1% managed to eat one after it blasted them in the mouth. Then they tried offering dead beetles. Still, only 14.3% of the frogs were willing to go through with eating them. So, yeah, not a popular snack. Next up, toads. Toads did swallow the beetles, no hesitation, but 43% of them ended up puking them out anywhere from 12 to 107 minutes later. And get this, all the beetles they barfed up were still alive and kicking. Bigger beetles were more likely to escape, and smaller toads were more likely to throw them up, basically being big helps, whether you are the bug or the toad. Now for the heavyweights, American bullfrogs. A whopping 96.3% of them flat out refused to swallow bombardier beetles. 88.9% stopped attacking right after getting blasted. 7.4% backed off even before getting hit. Only 3.7% actually managed to swallow and digest one. But here is the twist. When the scientists offered beetles that couldn't shoot chemicals, 77.8% of the bullfrogs swallowed and digested them just fine. Fast forward to the early 21st century, researchers at the University of California took it a step further. They used deuterium, a hydrogen isotope, to label synthetic chemical mixtures, then injected those into beetles and analyzed the spray using a mass spectrometer. They found two nasty chemical compounds known as phenols. One was a known product of hydroquinone metabolism, but the other was a brand new find, memcresol, a toxic compound commonly found in coal tar. And, yeah, these are bad news for humans. They're known to cause cancer, genetic mutations, and serious eye and respiratory damage. Here is even a real medical case. An 11-year-old boy tried to toss a bombardier beetle onto an anthill, but got sprayed in the eye instead. He suffered second-degree burns on his upper eyelid, and his eye's conjunctiva and cornea were severely damaged. Thankfully, after 2 weeks of treatment, he recovered. But let that be a warning. Just because it's tiny doesn't mean it's dead harmless. If you ever see a bombardier beetle, don't try to pick it up or squash it. Just gently shoo it away and let it go about its explosive little life. Jeffrey Dean, a biology professor at Cleveland State University, and his research team were the first to propose the qualitative passive pulsed ejection model. Jeffrey Dean suggesting that the bombardier beetle's spray is not continuous but released in discrete pulses. In 2015, materials scientist Eric Arndt from Massachusetts Institute of Technology conducted experiments at the Argonne National Laboratory. Using high-speed synchrotron X-ray imaging technology, cameras captured internal abdominal changes in the beetle during spraying at a rate of 2,000 frames per second. The resulting detailed images revealed, for the first time, how the spraying mechanism operates, confirming the model proposed by Dean's team. In humans, flatulence is caused by gas produced when gut bacteria ferment undigested food. You can carefully time the release by adjusting your valve and pretend to blame someone else, but you can't control when or how much gas is generated. The bombardier beetle, on the other hand, is able to control both production and release at will. It achieves this by using a flexible membrane valve structure and a channel between two internal chambers to regulate the pulsed spraying. The valve contains elastin, a rubber-like protein which enables it to remain sealed throughout each explosive discharge, much like rubber gaskets used in engineering valves. The passage between the storage chambers and the combustion chamber opens and closes passively. During an explosion, increased pressure causes the membrane to expand and close the valve. When the liquid is expelled and the pressure drops, the membrane relaxes and returns to its original shape, reopening the passage to begin the next pulse. This means that the beetle doesn't rely on muscular contractions to rapidly open and close the valve. Instead, the system functions mechanically, with an average pulsing frequency of 500 to 1,000 times per second, an astonishing speed. The pulsed nature of the spray helps protect the internal structure of the explosion chamber, allowing the chamber walls to cool slightly between pulses. The explosion mechanism used by the bombardier beetle produces spray That is, not only significantly hotter than that of other insects using similar chemical irritants, but also ejects the spray 5 times faster. Understanding how the beetle survives such intense internal explosions could inform the development of future explosion-proof systems. The kinetics of the spray process may also offer valuable insights for propulsion system design. A research team at the University of Leeds successfully propagated the beetle's thermal-chemical spray mechanism. They developed a system capable of ejecting spray pulses up to 4 meters with precise control over droplet size. The technology has since been licensed for industrial use and may offer a more energy-efficient mechanism for automotive fuel injection. It also has potential to inspire a new generation of fire extinguishers capable of generating fine mists or large droplets on demand. Inspired by the bombardier beetle, scientists have developed a biomimetic-shaped memory aerogel with aligned microchannel structures. When in contact with blood, this aerogel rapidly expands within the wound, forming a strong physical barrier that seals the bleeding site. It has demonstrated excellent hemostatic performance in treating severe hemorrhages. The bombardier beetle's spray system bears a striking resemblance to the pulse jet engine used in Germany's V-1 flying bomb during World War II. In 1944, the Nazis launched heavy bombing campaigns on London using the V-1 bomb, an early type of cruise missile developed as a so-called vengeance weapon. Once launched, it required no pilot and flew autonomously until it ran out of fuel and crashed, detonating on impact. The Germans nicknamed it the Bull Hellhound due to its terrifying presence. Its simple pulse jet engine operated at a pulsing frequency of 50 times per second, producing a distinctive buzzing sound during flight, hence its allied nickname, the Buzz Bomb. There are no historical records showing that the V-1's designer, Madelung, or any of his team had studied bombardier beetles. However, engineers at the time were deeply interested in biomimetics, drawing inspiration from nature for technological innovation. In their desperation to win the war, the Nazi military conducted numerous secret experiments. The film Overlord depicts some of these, including attempts to create invincible soldiers. Folk legends surrounding Nazi flying saucers, or the so-called Nazi Bell, are even more fantastical. If Germany's pulse jet engine design had indeed drawn inspiration from the bombardier beetle's defense mechanism, it wouldn't be surprising. As we've discussed earlier, the beetle's fuel chamber and reaction chamber resemble those in rocket engines. Notably, hydrogen peroxide, a known rocket fuel, is also produced by the beetle's glands. The beetle even rotates its spray nozzle to aim, similar to a rocket's gimbaled thrust system. Could rockets themselves have been inspired by bombardier beetles? Let's dig deeper. Wernher von Braun, the chief architect of the Saturn V rocket, previously led the development of Nazi Germany's V-2 rocket, a very different design from the Saturn V. Interestingly, Georg Hans Madelung, involved in the V-1 program, also contributed to the V-2 project. Curiously, Saturn V's design philosophy diverged notably from the V-2, but bore uncanny similarities to the V-1 in certain mechanical aspects, particularly those aligned with the beetle's spray mechanism. This leads to the question: could von Braun have been indirectly inspired by Madelung's work, and possibly by the beetle itself? In 1931, von Braun met a surgeon named Dr. Generals, with whom he conducted simulated lunar experiments using rats. Remarkably, in 1960, they published the results of their work in the New York State Journal of Medicine. For a man who could spend 2 or 3 decades experimenting on mice for the sake of science, the idea that he might have studied the bombardier beetle seems entirely plausible. At the time, it wasn't just the Germans who were developing rockets. The United States was also actively pursuing rocket research. In 1936, Theodore von Karman, director of the Guggenheim Aeronautical Laboratory at Caltech, launched a small rocket program by recruiting 5 young men to form an amateur rocketry group. Among them, Malina and Bollée were von Karman's students. Smith was his assistant. Parsons, a chemist, and Foreman, an engineer, came from outside Caltech. The five quickly dove into ambitious research. Some were even envisioning lunar landings. But within just a month, they were on the verge of disbanding due to a lack of funding. Desperate, Molina and Parsons turned to writing science fiction in hopes of generating income. Their novel told the story of an evil rocket scientist aiding a tyrannical emperor in his quest to dominate the world. After months of effort, however, they didn't earn a single cent. A year later, a student studying meteorology came up with the idea that rockets could be used in atmospheric science. He managed to scrape together $1,000 from various sources, giving the team a much-needed lifeline to continue their research. It was during this time that von Karman convinced another one of his students to join the rocket group, a Chinese scholar named Qian Shushen. Many of his most important early research papers and technical notes were completed during this period. As the number of published papers grew, this amateur rocketry group began to attract more attention from the university. Caltech eventually decided to bring the team under the umbrella of the Guggenheim Aeronautical Laboratory, officially assigning them a basement lab for their experiments. However, less than a month later, the school kicked them out, because one of their explosive experiments nearly blew up the entire aeronautics building. Once again, good old von Karman had to pull strings all over campus to keep his students from being expelled. Eventually, the university relocated the group to a remote area outside town in the Arroyo Seco Valley, a place that would later become the Jet Propulsion Laboratory we know today. Their quirky team earned all sorts of nicknames: the Suicide Squad, the Powder Gang, the Caltech Kamikazes. Among them was Jack Parsons, a brilliant chemist who also believed in black magic. He was fascinated by the idea of traveling to unknown realms through mystical means. At the same time, he was also a devoted insect enthusiast. Perhaps as these wildly imaginative young minds conducted experiments day after day in the valley, someone really did catch a bombardier beetle and maybe even studied it, if only by accident. In 1954, the Jet Propulsion Laboratory teamed up with Wernher von Braun, the Army Ballistic Missile Agency engineer, to prepare for launching a satellite into orbit. Von Braun, of course, is the German engineer we mentioned earlier. And if we connect all the dots between the engineers who were involved in early rocket design, we'll find one curious shadow always lingering in the background: the Bombardier Beetle. Perhaps the design of the liquid-fueled rocket really was inspired by the farting beetle. In 1958, with von Braun's support, the U.S. Department of Defense approved funding for Project Orion, starting with $1 million per year. This was a bold scientific plan to study the feasibility of a nuclear pulse propulsion spacecraft, a ship powered directly by a series of nuclear explosions behind it. The Orion nuclear pulse drive could theoretically combine exhaust velocities of 19 to 31 kilometers per second with megaton-scale thrust. Many existing propulsion systems can achieve either high speed or high thrust, but the nuclear pulse rocket was one of the few concepts that could potentially deliver both at the same time. The plan even proposed the design of a Starship 400 meters in diameter, weighing around 8 million tons, large enough to house a city of 100,000 people or more. This massive ark would act as a civilization backup, a refuge in case of global catastrophe. It was imagined as being capable of traveling at a significant fraction of light speed, making interstellar voyages to nearby star systems. Eventually, the project was shut down due to concerns over nuclear fallout. But don't be too surprised by the wild imaginations of scientists. Perhaps one day, a spacecraft that continuously nuclear farts its way through space really will carry humanity to the stars. And who knows, maybe it'll even be shaped like a bombardier beetle, in tribute to the unlikely insect that sparked it all. How did the bombardier beetle evolve such a sophisticated chemical factory inside its body? The truth is, it's still a mystery in the scientific world. Some scientists have proposed that insects may have traveled through space to reach our planet, and that Earth's insects might one day make the same journey. leaving our world behind and heading toward distant stars in the galaxy. This theory could even help explain how life originally began on Earth. It's based on British scientists' research into powerful interplanetary dust streams, which can travel through space at speeds of up to 70 kilometers per second. According to their calculations, tiny biological particles floating in Earth's upper atmosphere, 150 kilometers above the surface or higher, could be knocked out of Earth's gravitational pull by incoming space dust. These microscopic organisms might eventually reach other planets within the solar system. Some bacteria and plant spores are even known to survive in the harsh conditions of space, and if this can happen one way, it might also happen in reverse. Alien insects could have been carried to Earth the same way, helping to seed life here long ago. Entomologist William Romoser presented a controversial poster at the annual meeting of the Entomological Society of America in Missouri, claiming that he had found compelling evidence of life on Mars, including images of insects and reptile-like creatures, some of which he argued were still alive. His critics, however, dismissed these claims as examples of pareidolia, the human tendency to see familiar patterns in random shapes, like faces in clouds or pancakes that look like the Virgin Mary. Creationists, on the other hand, view the bombardier beetle's precise and complex defense system as proof of divine design. They argue, how could a defense system so intricate evolve step by step when its incomplete versions would have been useless or even dangerous? Others have an even wilder take. They say the bombardier beetle is an alien-designed mech, deliberately left on Earth for humans to study, because its biology simply defies evolutionary logic. Maybe 400 million years ago, this insect really was capable of interstellar travel, powered by the chemical factory inside its body. Over time, it may have lost that ability. But perhaps even now, these beetles are still trying, experimenting day by day, hoping to reawaken their forgotten gifts. And maybe their mission is best captured by the personal motto of Jack Parsons, the brilliant, eccentric chemist of the Suicide Squad: Per aspera ad astra. Through hardship, to the stars.